should probably say, I want to do a quiz, your next quiz, and I want to do it on Wednesday. I want to do it Wednesday of next week. So that'll be on these lectures and on the lecture you get Monday. Probably mostly on Monday because that'll be the material freshest in your mind. If you're wondering about your tests, I'm almost done with them. My 6-year-old daughter got sick this last weekend, so I was not able to finish them. So you're not getting them back today, but you'll probably get them back Wednesday, and if not Wednesday, you'll get them back next Monday for sure. I almost never go over more than 2 weeks with tests. So, if you have some reason why you need to have that, like super quick, like you're thinking of dropping the class or something and you need to know what you made on the test, shoot me an email and I'll try to get yours done and just get in touch with you super quick. Let me pick up with this because sometimes this lecture gets kind of involved. I told you last time I really like the part of the class that we're in now. I can spend all day talking about this stuff, so I'm not going to do that to you. You don't have to worry about it. But if I start going too long, somebody kind of give me the little sign to keep moving with it. When we left off last time, we had talked about like boats and ships and maritime stuff, going all the way from the dugout canoe through the 19th century, through the mid-19th century. And so I'm picking up today right where I left off. Last time we talked about how after Trafalgar, you get the apex of sailing technology. The apex of sailing technology looked like that, if you remember. Acres and acres of canvas sails on ships that were called the clipper ships, capable of doing things like sailing from Great Britain to Australia in 3 or 4 weeks. Which was remarkable for the world in their day. Capable of using the prevailing trade winds, something called the Roaring Forties. A ship like this could make the passage really quickly. And so where I'm picking up is where I left off last time, which is right about the 1840s and 1850s. We're going to get a technological revolution. Now, a lot of times people talk about technological revolutions and they get all tangled up with questions like, at least academics do, were these changes revolutionary or evolutionary? Were these changes really quickly occurring, or would you categorize it as more of an evolution? I think those sorts of questions, while they're interesting, they're not really pertinent to what you're doing here. And so I'm just going to tell you my opinion. This is a revolutionary change. The 1840s and 50s, it's true that this is not overnight, but this changes everything and very rapidly. What we're getting with these technological revolutions at sea in the 1840s and 50s, revolutions in propulsion, and a connected revolution in construction. Now, since I've been talking about boats and ships since last lecture, all the ships were made of wood floats, right? But in the 1840s and 50s, they start to experiment with metal ships made primarily out of metal. And the way that they do this at first is experimental. It's not a really well understood thing how you're going to be able to create a ship out of metal that is able to sufficiently keep the water out and keep the ship afloat. It's difficult to do these sorts of rivet work, for example, that'll keep the water out sufficiently to keep your ship from flooding. So the first few efforts to do this largely meet with failure, especially regarding things like warships. Because in the 1840s and 50s, what they're primarily trying to use is iron. And if you know some of the characteristics of iron, you know that if you put iron in a marine environment, what's going to happen? Rust, right? Super fast. That's a problem that they have. Another problem that they have is that if you're building a warship out of an iron hull, primarily, what you're going to end up with is something that, while it may be very hard and tough, it can also be rather brittle. And so the British especially are really concerned with this, and they're experimenting with various iron-hulled warship designs in the 1840s. This is a picture of one of them called HMS Gorgon, G-O-R-G-O-N. It is a steam-driven, paddle-wheel, iron-hulled warship. What they find with this type of design, though, when they're testing the iron plates that they make the hull out of, is that if that iron plate is struck with a cannonball or something like that in a battle, the plate fractures. And it fractures in such a way that the crew can't shore it up. They're not able to shore up the damage in the same way that you could with a wooden hull. And so there's a period of experimentation. The solution that they hit upon is that if you back the iron with a wooden frame, in other words, you build a wooden ship and then you cover it with an iron sheathing, that gives you the best of both worlds. It gives you the ability to waterproof the thing fairly well, and yet to provide some form of metal protection for that wood against potential attack. So they're going to start to approach understanding how to do this in stages. That's your construction revolution. They're starting to use metal. They're having more high-quality metal available because of the Industrial Revolution, and this is one application of it. And the second thing, this revolution in propulsion, we're really talking about coal-fired steam boilers being put in ships and using those as the propulsive mechanism to move the ship through the water. A couple of things we need to talk about with this whole thing. If you take a coal-fired steam engine and you put it in a ship, which is made of wood planking covered with an iron hull, you've got some potential for problems, right? The wooden planking can catch on fire. All the heat generated by that steam engine inside the hold is not really going to do so well. There are examples of these early steam-driven ships that burn to the waterline because of that very issue. There are problems with overly pressurized steam boilers. They don't regulate it properly. That thing can turn into a giant bomb. It can blow the ship apart under steam pressure. Other problems. You've got this giant funnel, as it's called on a ship. Most civilians would call it a smokestack, but it's a funnel on a ship. This funnel taking out the coal smoke from the burning steam engine, but within that smoke are still glowing cinders and embers. This technology does not fully burn the coal as fuel, and so these glowing embers, which are coming out in the smoke, tend to have a problem. They'll hit the sails and potentially burn the whole thing down. Again, there's all kinds of problems. Problems that most people don't even think about. One of the biggest problems has to do with vibration. You've got this steam engine, it's chugging away and it's building up steam pressure. The ship is being acted on by the motion of the water around it, but you have this problem with vibration in the hull of the ship as the steam engine's working. Vibration tends to work loose rivets and joints and open up seams and cause flooding. So this technology, it's got some problems as they're trying to innovate and adapt with it. And so you see this really weird period in history. Like if you're just looking at these kind of images, you're like, it's strange. They've got steam power, and they're starting to experiment with metal hulls, but yet look at the ship. It's still got the full sailing rig. And the reason for it is that they don't fully trust this technology yet. The reason is that they're looking at it and they're saying, this seems like the way of the future. We maybe have reached a point of closure here, at least it's in sight, but we're not fully confident in it. We're going to retain the old sailing rig just in case. And that's especially going to be true for the British Navy, because the British Navy has global responsibilities in the 1800s. They rule the waves of the world. And so you cannot, as the British Royal Navy in the mid-19th century, just jump wholeheartedly into this whole steam revolution thing, right? Frankly, because a ship like this, if it's dependent upon coal, you have to have a network of coaling stations worldwide for this thing to stop off at and retop its coal bunkers. And so as a consequence, they say, well, we'll use this when the situation's appropriate, but we're going to retain the sailing rig because that's what has allowed us to maintain this maritime empire for centuries. A few other things I want to say about the technology. If you look at that particular piece of technology, the paddle wheel on HMS Gorgon, spinning round and round, you've probably seen something like that on a riverboat in this country. Some problems with that, on a warship especially. If you remember what I told you last time, I told you that they mounted the cannons along the long axis of these ships. In other words, the guns point out the side on both sides. So what you've got, if you mount one paddle wheel, is a tremendous, complicated piece of machinery that is obstructing about a third of your potential broadside on the starboard side in this particular case. Right? Your paddle wheel's mounted here, it's churning round and round. You can't mount guns right behind that. Okay, that's one problem. Admirals and ship captains don't like having their firepower reduced just because you have this piece of machinery twirling round and round and splashing in the water a lot. The second thing we could say about it, if you just look at it, it's vulnerable, right? I mean, anybody with a cannon firing at that thing, you shatter one of the spokes on it, it's completely useless. And so ship designers in the 1840s and 50s are looking at this paddle wheel thing. They're saying this works for river boats and for people cruising up and down, gambling on the rivers and things, not so much for a warship. And so they're looking for something that they can harness to a steam engine that will not obstruct their field of fire, that will not be vulnerable to counterfire as easily. And so what they hit on is something called the screw propeller. And it's this, right? You mount it below the water line near the back end of a ship. As it spins round and round, you can go in forward or reverse with it, and you're going to use this as the primary means to propel your ship. Now for people who are like, great, I can check that off, I understand it, we can move on. We can get into so much detail here. I won't do it to any of you, it bore most of you. But you have a problem here, for example, in that, how do you do this? You take a metal shaft running to the screw and in through the hull. Well, you have to have a hole bored through the hull of your ship for that shaft to pass through. How do you waterproof that? How do you keep that from being a place where water leaks into your engine room and floods your ship? It's really a difficult problem at first, especially because these steam engines chugging away inside the ship's hull are generating so much heat that they cause wood to swell and warp and cause all kinds of problems with this at first. It's not really going to be until 1850 that these problems get solved. In 1850, you have a breakthrough moment. Ironically, the technological breakthrough is not with the British, who are the premier naval power of the day. It's with the French. It's France that develops the world's first all-purpose, steam-driven, coal-fired battleship. And if you look at it, you say, well, that looks a lot like HMS Victory from the slides last time. Of course it does. It's a 3-decked wooden warship with iron on the hull. It's got these coal-fired reciprocating engines, but it still has the full sailing rig. Napoleon, built in 1850. Why don't the British innovate here? Why are they not cutting edge, leading the way? The answer is that for the British, this steam engine technology represents a question mark. I mean, they're ready to adapt it if it's shown to be workable, but the British already have sea power in 1850. For them, this is a case of wait and see. If somebody else can pour all the money and innovation into making this technology work, the British are standing by ready to build lots of these things. But the British are not going to undercut their existing superiority, the supremacy that already is theirs. They're not going to undercut that by saying, let's technologically innovate and change the game up. They're already winning the existing game. So they're standing by and waiting. The French, who are trying to cut in on the British lead, they're the ones innovating. They're the ones who create this, make it work. The British look at this, and within 2 years, the British have built multiple ships of this type. The British just outbuild the French once the French prove the concept, basically. And so we get this really strange period in the mid-19th century continuing. The mid-19th century is weird for technology, especially military technology, because there's not lots of major wars. You've probably heard that the century between 1850 and 1914 has been called the Concert of Europe, because there weren't many major wars in that time. And so one of the major wars that was fought is the American Civil War, and it became kind of a testing ground for the technologies that existed. And in terms of naval stuff, in terms of maritime technology, the most famous technological innovations of the American Civil War were these, ironclads. Well, what is an ironclad, really? It is a wooden ship which is covered in metal. I mean, we've seen that in Europe already, right? This is the evolution of that idea, sort of taking it to a new level. And what you can see with these two Civil War era ironclads, you have the CSS Virginia, formerly USS Merrimack. The Confederates captured the wooden-hulled warship Merrimack in the Norfolk Navy Yard. They refitted it over a period of about a year. They covered it in a plate of armor. They turned it to a casemate battery, which means that you have these guns lined up inside the upside-down bathtub-looking thing. Stuck a steam engine in it, you have an ironclad. At the same time in the north, you have the construction of this ship, which people at the time said looked like a cheese box on a raft, very low to the water design, called USS Monitor. USS Monitor was really the cutting-edge technology between the two. Something like CSS Virginia is basically just an armored version of an existing battleship. The guns point out the sides. There's no masts and sails, but it's a pretty standard idea. Monitor is pretty cutting edge though. USS Monitor, designed by John Erickson. And the reason it's so cutting edge is that Monitor only mounts 2 guns, just two cannons. They are 12-inch naval Dahlgren rifles, and they're both mounted in this revolving turret, right? So you've got this very low to the water ship, and that's a problem for Monitor later. It's got a revolving turret. These 2 ships meet in a duel, the first duel of ironclads anywhere, in Hampton Roads, Virginia, just off Norfolk. They're going to meet in 1862, and the result is inconclusive. It's a draw. What ends up happening with these 2 cutting-edge vessels? I mean, people talk about this. They write books about it. They've made movies about it. Such an incredible moment, clash of high technology, 1862. Well, neither defeats the other in the battle. They both bounce cannonballs off the iron hulls of the other ship. And at the end of the day, what happens is that nothing has really changed that much. It's a draw. Later, the Virginia is going to be scuttled and burned because the Confederate Army has to retreat, has to abandon Norfolk. And the Confederates can't get the Virginia over the sandbar in the James River to escape. And so to prevent it from being captured by the enemy, they burn it to the waterline. USS Monitor, after the duel, it sails out of the harbor, and it's trying to make its way down the coast of North Carolina. It's in a storm in the open ocean, and it capsizes and sinks off Cape Hatteras. In fact, they've just recovered some parts of it recently. It's not seaworthy at all. I mean, the thing has a freeboard of about 1.5 feet. Just about 1.5 feet above the surface of the water is where that deck is. So it's not really seaworthy by any stretch of the imagination. I want to talk about another type of technology in the Civil War that really starts to gain traction. Some of you have probably seen this, so this is one reason I include it. Submarine warfare. A lot of Americans falsely believe that the Hunley was the first submarine. That's actually not true. The first submarine used for military purposes was in the American Revolution. There was an American submarine in the American Revolution of the 1770s called USS Eagle. USS Eagle. USS Eagle was a beer barrel with a little hand-turned propeller and a little screw on the other end. And the idea was that by climbing into the beer barrel and sealing the lid, you could put the thing into Philadelphia Harbor, and somebody sitting on a bench inside the beer barrel could crank the handle and move the beer barrel just below the surface of the water next to a British warship, and then you would bore a hole in the hull and sink it. That actually didn't happen, obviously. The Eagle went out, it was bobbing along in the harbor, and the tide carried it out into the open ocean, where they had to rescue the crew with a rowboat. It was a complete fiasco. By the 1860s, they're a little more serious about this underwater thing. The Confederates, being a naval power which does not have the industrial might of the North, has to rely on cutting-edge technology, on innovation, to try to gain an advantage, right? And so for that reason, it's the Confederate Navy that does things like developing the first functional submarine. They don't have the ability to build big warships like the North does and triumph that way. So they're trying to leverage technological superiority to make up the difference. CSS Hunley is an example. So the Hunley has space for roughly a dozen men inside. They all sit on benches. If you've been to the museum, you've seen it. They turn the little hand crank, which turns the propeller, moves this thing along below the surface of the water. Now the way that something like the Hunley is supposed to sink a ship is that it goes up right next to the ship and it attaches this spar torpedo. There's a little harpoon on the end of that thing. You punch it into the hull of an enemy ship, and then your guys on the crank start reversing, and you back up. And as you back up, this breaks off, and that charge remains affixed to the hull of the enemy warship, and when the wires pull taut, it initiates a charge, blows a hole in the enemy ship, and sinks it. And this actually works. Hunley is the first submarine to ever sink an enemy warship. It sinks the USS Housatonic off the Charleston bar late in the Civil War. This Housatonic is trying to blockade the harbor along with several other Union warships.
What's the name of the ship again?
Housatonic, Housatonic. Housatonic. Housatonic sunk by the Hunley. We're not quite sure what happened to the Hunley. It never returned from that mission, but it's a good bet that as Hunley approached and attached the spar torpedo to Housatonic's hull that night and started backing off, the explosion went off. Housatonic started to go down, started to founder, and when ships sink, they tend to create a vortex or a suction. Very likely that Hunley just got pulled down along with its intended victim. But Hunley doesn't come back. So it does have the start of submarine warfare, something we're going to be talking much more about in just a minute here. So after the Civil War, there's this super weird period. I've talked about this a little bit, but it's weird because if you look at these ships, they are modern in some ways. This is USS Chicago in 1880. It's an all-metal warship. They figured out that metallurgy has reached a point by the 1880s where they figured out how to fully construct the hull out of metal. You can see that they've gotten somewhat away from this whole internal guns running the length of the ship, although you can see they still have a few. Instead, they're starting to go with these sponson mounts, which are basically like little mini turrets, almost like you'd see on the monitor. They're trying to combine some technologies here. You can see that the steam engines on the USS Chicago, pretty powerful. I mean, they've got 2 funnels now, so they're drawing a pretty fair amount of air, and they're putting out good horsepower from these engines, but you can see what remains. You've still got these masts, because the navies of the world are still not fully willing to take that leap and say, we're just going to go completely with coal-fired steam engines. We're in this sort of halfway point. This is like a bridge technology, one way to think of it, right? So by 1905, that's changed. By 1905, you start to see warships come out which don't have those masts and spars, no sailing rigs anymore. And an example of that is the British warship HMS Dreadnought. HMS just stands for His or Her Majesty's ship, the Dreadnought. And 3 things about the Dreadnought, which we'll talk about in this class. The first is that they've gone over to a fully steam-driven propulsion technology, steam turbine engines. And for those of you interested in this level of detail, the Dreadnought in 1905 is not making use of coal anymore. They're using oil-fired engines to develop the steam they need and create the speed that they want. Dreadnought is a very fast ship. Even in open waters, the Dreadnought is capable of doing about 27 knots sustained. So that's 40 miles an hour, roughly. About 40 miles an hour for a ship that weighs tens and tens of thousands of tons. It's so heavy because of its heavy annealed armor. Annealed armor just means that you're taking different types of metal and you're laminating them. You're sandwiching them to create super hard armor. So they'll take inches of rolled steel and they'll back it with nickel and then other types of metal to create extraordinarily hard armor for something like this, inches and inches thick. I've had students ask, well, where are they armoring? The answer is in the key locations. They have what's called the armor belt that runs along the hull of the ship near the waterline. It's supposed to protect the ship from fire that's coming in near the waterline, potentially holing the ship. So they've got this armor belt that runs here. And then other critical areas of the ship are armored. So like the magazine where they store the ammunition, that's armored. Your bridge today where your combat information center and things would be, that's all going to be armored. It's where the ship is fought from, where your captain and various officers stand directing things on the ship. These ships can potentially be destroyed by gunfire. They're fairly vulnerable to something called plunging fire, which is if you have 2 ships of a similar type and they're blasting away at each other. This happens notably in 1916 in a battle called Jutland. You've got these ships firing at miles and miles. They're trying to use what's called plunging fire. And any of you play World of Warships already know what this is. You fire these shells that arc through the air and they're dropping at a fairly high angle onto the ship from above. And the deck is not armored at all. It's made of wood. And so if you can punch a high explosive shell through the unarmored deck into the innards of this thing and hit something like, say, a magazine, you can completely destroy the entire ship. So even though it's very heavily armored, there are vulnerabilities to it. Last thing I want to mention about these new ship types is the gun styles that they're using. By 1905, they've gone completely with that turret design. A ship like this has no guns, which are fixed and pointing out the side. Instead, its guns are all contained within these armored turrets. The turrets have an arc that they can be directed in. So it's not a 360-degree arc. I mean, like for this gun, for example, they could direct it from about here through the range of motion, through the degrees, to face back about like that. But the ship's superstructure would be in the way of a full 360-degree sweep or swing. For those of you interested in this sort of detail, how big are these guns? How good are they? Dreadnought makes use of 12-inch naval rifles. It means that each gun has a bore diameter of 12 inches. It's firing a shell about a foot across. It's rifled, which means it's very, very accurate, long range as possible. Each of the shells fired by a ship like Dreadnought weigh as much as a Volkswagen Bug, a Beetle. And they can shoot those shells for 30 miles, roughly. You're wondering, was that ever possible? Was that ever actually done? The answer is yes. A British super dreadnought battleship in 1916 at Jutland, HMS Warspite, holds the record for distance of a ship like this firing a shell and hitting an enemy ship. And Warspite at Jutland in 1916 fired that shot at 27,000 plus yards. That's a long ways. That's over the horizon. The way that they do that, you have a few guys, whose job is to be in the fighting top, high-powered binoculars, and when a ship like this fires the broadside, all of its guns, these guys are watching with binoculars for the fall of the shot. And as they see the splashes way off in the distance, and then they correct the fire for the gun crews, and they try to maneuver it properly so that they put their fire on target intended. That's HMS Warspite, firing in the years just before Jutland. If you're interested in this sort of stuff, you can go on YouTube and watch hours of footage of battleship broadsides. Really impressive stuff. When a ship like this fires a full broadside, the entire ship, massive as it is, it just rolls in the water. It's a massive, massive recoil. I want to return a little bit to this issue of submarines, because submarines are going to really be, in my opinion, the naval technology of the 20th century, and into right now, actually. So when we talk about submarines in the time since the Civil War, there have been a lot of advances. You've got advances in propulsion, primarily. In the late 1800s, early 1900s, they got away from the little hand-cranked propulsion thing. There was an American named John Holland. John Holland built the world's first modern submarine. In fact, then President Teddy Roosevelt was the first American president to go down underneath the surface of the water in a submarine. It was John Holland's number 1, is what it was called. It was an imaginatively named submarine, number 1. John Holland's number 1. So the technology in which you have electrical batteries being used to run electric motors and propel a ship under the surface of the water was available in the early 20th century. A student once asked me, well, why didn't they run with steam engines? And why couldn't they run a submarine on that? And the answer is pretty obvious. You're in a closed container under the water. There's nowhere to vent that coal smoke to. There's nowhere to vent the exhaust if you're using something like a diesel engine. So these submarines in the early 20th century actually have two types of engines to propel them. You've got a diesel engine that you can run when you're on the surface. You just vent to the outside air. As soon as you go down below the surface of the water, you have to cut the diesel off and switch over to battery power. You're switching over to an electrical motor to propel your ship forward, because you have nowhere to vent any sort of exhaust fumes to. What you end up with this is a situation in which these submarines of the early 20th century, they can only stay submerged for about 10 to 12 hours and remain underway. They burn their battery power up after that. They have to surface after about 10 to 12 hours of running submerged, because they've got to get that diesel engine cut back on and recharge the batteries. Their time beneath the surface of the water is actually really limited. And so there are historians who will tell you that these early 20th century submarines, you have to think of them more as torpedo boats, which are capable of being submerged for a few hours at a time. They're not like submarines today at all. So the Germans take this technology of the submarine and they really run with it. This becomes, for about half of the 20th century, this becomes a German technology. The Germans do the best with it. And it's largely, again, a matter of necessity. The British have the largest battle fleet in existence. The British dominate this kind of fighting. The Germans can't catch up with this. The British are building battleship after battleship. They've already got a lead. They're already ahead. And so the Germans are going to turn to cutting-edge new technology to try to change the rules of the game up. And so the Germans, in the first few years of the 20th century, build lots of submarines, which are called Unterseebooten. And if you don't speak German, that just means undersea boats. Unterseebooten, or U-boats, German submarines. And the Germans combined their U-boat with a new style of weapon, which has really come into its own, the locomotive torpedo. Today we would just call it a torpedo. It's an elongated metal tube with several hundred pounds of high explosive in the nose. You use compressed oxygen to fling this thing out of a tube in the front end of the submarine underwater. As the torpedo clears the hull of the submarine, its own indigenous motor kicks on, and it spins these propellers, which moves the torpedo through the water. And the plan is that if you can impact the nose of that torpedo on the hull of a ship, you'll cause an explosion, put a hole in the ship, and sink the ship. So in
Just real quick about the torpedo.
Yep.
What type of motor or what ran their own propulsion system? Is it like a spring wound up or they have
They experimented with spring wind-ups. There's a guy named, he's a British inventor actually, his name's White. He comes up with something called the White torpedo, which is spring load, you wind it like a watch. It's a dismal failure. The thing has a range of about 200 yards, if that, and it's really slow. The Germans at the turn of the century start experimenting with compressed oxygen, and so they're running this thing off of compressed oxygen, which is turning a series of gears, and it's turning the props. Which is why these early torpedoes, when they're actually employed, you can see them coming. You see that trail of bubbles through the water? It's the oxygen being released as that torpedo is burning through. Yeah, no, that's a good question. Good question. We can be here all day. Yeah, I love talking about this stuff, right? So here's the thing though. This technology is super expensive. It's super expensive to build a torpedo because you're building basically a submersible, self-contained, high-speed weapon that's got to have gyroscopes and things in it to keep it from deviating too much, hopefully. It's really expensive. And so when World War I breaks out, these German submarine captains have a limited number of these things aboard. I mean, submarines are cramped anyway. They're tiny inside. They can't really contain too many of these. And so German submarine captains are like, well, what do we do when we come across a British merchant ship in the opening months of the war? Well, you surface the submarine, and because it's a gentleman's war, you get on the megaphone and you say, you have 15 minutes to get your crew to the lifeboats. After 15 minutes, you use a deck gun, and you put a little hole in the side of the ship, and the ship sinks. Very cheap, very easy to do. In 1915, the British develop what's called the Q ship. The British get wise to this, and they start mounting guns on merchant ships, and they cover them over with a tarpaulin. So in 1915, when a German submarine pops up, and the captain says, you have 15 minutes to get to the lifeboats, the British crew runs out, pulls the tarpaulin off, and tries to sink the submarine. And so these German submarine captains, in 1916, they go to what's called the no-warning sinking technique, where they don't play the gentleman's game anymore. They raise their periscope from under the water, they see a ship, and they try to torpedo it.
So you mentioned earlier that they had about 12 hours underwater before they had to come back up.
Yeah, depends on how fast they're running that engine and burning through the batteries, but yeah, 12 hours.
Was oxygen not an issue with
It gets to be a real issue after about 12 hours.
Okay.
Yeah, there are cases in World War I where German submarine captains record in their diaries, and they'll talk about how they tell most of their crew, go lay down in your bunk and don't talk, don't move, because the air is already getting really heavy is the word they use, but they're talking about the air becoming increasingly full of carbon dioxide and things. Yeah, it's not a healthy environment to be in, absolutely. So you've got this situation in 1916. Gentlemen's rules end. The Germans start doing no warning sinkings on ships because of the British Q ship technique. This is really important to world history, actually. I can connect this to a much larger thing than just technology, because in 1916, there was a German submarine captain. His ship is U-20, if you care about that detail, U-boat number 20, U-20. Sitting off the western approaches to Ireland. The Germans are trying to blockade the British Isles. And this German submarine captain sitting off the western approaches, he and his crew, they don't have sonar really yet, but they can hear through the water the sound of a very large ship passing by. And so this German submarine captain raises the periscope, and in his diary he says, I couldn't really see the ship. It was a foggy morning, but I could see it was a large ship. I got a glimpse of it moving through the fog at distance. He fires 2 torpedoes. The 2 torpedoes both hit, And the ship that he has struck is a cruise liner called the Lusitania, right? Lusitania goes down, about 1,300 Americans are killed. They were taking a cruise vacation to Europe in the middle of a world war, not a great plan. You got 1,300 Americans killed. It almost, in the US coming into World War I, 2 years before we actually do, right? Major, major incident tied to this. I want to briefly talk about another development. Some people will argue with me and say, no, the biggest technical development in terms of ships in the 20th century was the aircraft carrier. I'm going to make that argument proven false here shortly, I think, but some people may still hold to that point of view. There are some points for both submarine or the carrier. First aircraft carrier in the history of the world is this ship. It's HMS Furious. It's a British design. Late in World War I, you've got the airplane. The British have lots of ships, and so it doesn't take a genius to say ships plus airplanes would be really awesome. Let's combine them somehow. So the first aircraft carrier is actually a battle cruiser. Got big guns on it. And in 1916, the British say, we have enough battle cruisers. Let's pull the guns off of Furious. Let's build a flat wooden deck on it instead and try to fly airplanes off of it. And so this picture that you see is taken from the fighting top of HMS Furious, looking forward, showing you all three of the aircraft they could mount on this thing. All three. All right? Now the way that you fly off of HMS Furious is this. You get your plane here, the pilot gets in, he starts the motor, and they take down this little fence thing and move the other planes out of the way. You've got your propeller spinning, the ship turns and sails into the wind as fast as it can. So the wind is blowing this way, which is going to give the plane some added lift. Everybody on deck is holding on to this plane. They've got ropes and things tied around it, they're holding on to it to act as a brake. And at a prearranged signal, as this ship goes down, it's called the down roll, as it goes down and reaches the bottom point of the down roll, they say, let it go. Let go of the ropes, the ship starts to roll back up with the waves, you've got the wind blowing in your face, and hopefully it helps your plane lift off safely. That's pretty easy. Most people in this room with probably a few hours of training and good luck could take off from this ship. Not too difficult. Landing on it is another matter altogether. Because what you have to do if you are a Royal Flying Corps pilot who's been assigned to the Navy is fly your biplane on a parallel course with the ship. And as you pass the superstructure, you're flying along, as soon as you get even with this thing, you've basically got to throw your stick to the right and kick right rudder, slide into your landing zone, and then drop down to the deck really fast. It's not safe. It's not a really good way to do it. And so there's lots of pictures of this as they experimented with it in World War I. And what you see here is this plane who has made his approach. He's slid into position, and he's trying to bring it down on a few feet of deck. And these are all petty officers and Royal Navy ratings. What they're all trying to do is grab a hold of the plane. Grab it, grab it. Quick, put the brakes on. They don't make it in this case. It goes over the edge of the ship. The pilot did survive this crash, but this is dangerous business, trying to operate planes off of ships at sea. So it's actually the United States that gets the answer to this, and we are the first ones to do it. The first real aircraft carrier that works functionally, that's able to do this sort of thing, is USS Langley. USS Langley, CV-1. The US Navy has sort of an odd way of designating ships sometimes. CV, the C stands for carrier, it's an aircraft carrier, and V means it's heavier than air. Because yes, in the 1920s, the US Navy is experimenting with using blimps to carry aircraft into war zones. So they have the CV. CV-1 is USS Langley. Langley was actually not initially designed as an aircraft carrier. During World War I, it was being built as a collier. It carried coal for supplying other ships. But as the war ended, they didn't need more colliers, and so they said, well, we've already built this thing mostly, but instead of just scrapping it and turning it into lots and lots of razor blades, let's go ahead and put a wooden deck along the length of the ship. What we can do then is we have a flight deck for flight operations. We'll put these elevators in the middle of the deck, and the planes can be lowered into this hangar, the hangar deck, just below the flight deck where the mechanics can work on them. They can be refueled and rearmed. When they're ready to fly again, we just bring them back up to the top deck and we continue to fly. So a few things about Langley. Langley was not extremely efficient. It was much better than what had come before, but its major problem were these things right here. If you're looking and saying, well, what are those? Those are stacks. Those are for venting the exhaust from the engines of Langley as it's underway. Why is that a problem where they're located? Well, if you're a pilot and you're flying in on final approach to try to land on Langley's deck, you're flying into these superheated gases that are roiling the air. It's giving you that mirage effect, and it's meaning that as your plane's about to touch down, you're going to get unstable all of a sudden. You're going to hit that unstable patch of air, and that's not a good place to hit unstable air as right as you're on final approach for an aircraft carrier.
Like, where's the bridge, or like?
Good question. The bridge is actually located right about in here. So they're like looking out from under the flight deck.
Oh.
There was some, the Navy at the time tried to sell this as, well, if we put the bridge here, it's protected from potential fire by the fact we have this flight deck above it. But this deck is made of fir beams. It's not going to stop any substantial fire that's incoming. So in the 20s, the US keeps experimenting, and we build these things. Now, these things, when you look at it, you're like, that's an aircraft carrier. The modern eye sees that and immediately recognizes it. The technology is evolving. Lexington, Saratoga, replacing the Langley. I love this picture because you've got Lexington, Saratoga, there's the old Langley sitting at dock. So you can see the Langley's pretty small by comparison. In the 1920s and 30s, they referred to these things as super carriers. They're all of like 700 feet long, right? They're nothing like the size of a Nimitz class carrier today, which is like 1,300 feet, basically twice the size of that. But that's pretty big for its day. What are some technical changes here, ones that I want to point out at least? You have a bridge superstructure. This is called the island, by the way. So if you go down to see the Yorktown and you see the superstructure and that giant funnel, it's called the island on an aircraft carrier. The reason for it is pretty simple. If you mount the stack high enough and off to the side, it means that pilots coming into land don't have to worry about that roiled air effect anymore. It's been cleared out of their line of approach so that they can make a landing more efficiently. The other things that these ships do that really sort of open the way for the modern aircraft carrier is that they have what we would call a resting gear on the back of the ship. You basically have 4 metal wires that run across the back deck of the ship. And this is how an aircraft is able to land on a ship and not run off the other end. Planes coming into land have a tail hook, metal hook in the tail of the plane as they're on final approach. What they're trying to do is snag the number 3 wire. It's considered a perfect landing. They got the hook. They're trying to catch one of the wires, which brings them to a stop before they fly off the front end of the ship and get smashed under. As I said a minute ago, I'm not going to take long on this, but it is kind of interesting. The US Navy in the 1920s does experiment with using lighter-than-air aircraft carriers and its blimps. USS Akron, this blimp right here, was the US Navy's test platform. They developed this gantry system, and what they would do on, like USS Akron, you have these little planes, these Sparrowhawks as they were called, and a pilot would crawl out along the metal framework inside the blimp, drop into the cockpit of the plane, turn the engine on, do all the pre-flight stuff, and when he was ready, this would open up and the plane would drop free of the blimp and it would fly off and do its mission. And then when it returned to the blimp, it would fly parallel to the blimp and the gantry operator would play like a carnival game with it almost, trying to grab this sort of a lattice work on the top wing. And if he succeeded in doing it, then they move the plane into the blimp and they repeat the process. They actually did get this to work. They got it to where it was fairly functional with a lot of practice, but what ended up being the weakness is they had several blimp disasters in the 1920s. You've got this giant bag of flammable gas, tends to cause problems even in the civilian world, but especially if people are shooting at you. That's not something you want to be in. And so this whole lighter-than-air thing proves a technological dead end. World War II, in many ways, in the Pacific at least, is a carrier war. This is a picture of USS Yorktown. So some of you have probably been on that at Patriots Point in Charleston. It is the development of carrier war. You have the ability by World War II to put 80 to 90 combat aircraft and fly them off of a carrier like this. You're able to have military campaigns that stretch across the Pacific. World War II is a carrier war in the Pacific to the degree that The act which brings the United States into World War II in the Pacific is the Japanese attack on Pearl Harbor, launched off of 5 Japanese aircraft carriers. The central battle of the Pacific War, Midway, is a completely carrier-driven battle. The two fleets don't ever actually sight each other physically. It's all the fighting is done by planes and striking at each other over the horizon. So carrier war becomes pretty important. Briefly, I'll talk about it. I will suggest to you, I've had people who will argue this before, but it's an interesting conversation. Who are the most skilled pilots in the world? And I will tell you without a doubt, in my opinion, they are naval aviators. And the reason is that Navy pilots, unlike people who have like 20,000 feet of runway to land on, a Navy pilot has, in this case, about 800 feet of runway to land on. And it's not just moving forward, it's rocking and moving up and down and side to side. It takes years to train people to do this. Very, very dangerous, even when they've been trained. Hours of footage on this on YouTube if you want to watch carrier landings. I've only done one carrier landing in my life. I was not the pilot. We're doing joint exercises with the Navy, and I got a chance to fly backseater in an F-18 Super Hornet, which is flying out to the Dwight Eisenhower, which was off of Norfolk at the time. When we landed, I mean, I remember looking forward at the Eisenhower, and it looked tiny in the ocean. I'm going to land on that thing. And of course, it's 1,200 feet long, but when you're in a jet that's doing 130 miles an hour, just above his stall-out speed before he touches down, that's a blur. And I remember when I got out, I said, how many times have you done this? And the guy that was flying me was the carrier air group commander, he's the CAG. And he's done this, 10, 12,000 times. And he's like, oh, that was nothing. He was like, you ought to do this with me when it's like raining and at night. I was like, no, don't think so. Got more guts than I do. Guts. F-6F Hellcat. This is USS Princeton, 1944. This plane has come in on final approach. It had some battle damage. So you can see what happened. The landing gear on the left side of the plane snapped off, damaged in battle. So the plane kind of skewed off and almost slid off the side of the ship, but it hasn't slid completely off. There's a pretty good fire going. This enlisted deck crewman, I mean, the guy deserves a Silver Star minimum in my opinion. Look at that. You got this fire going, that's a fuel tank he's climbing on. He's getting up there to try to get that pilot out. He's not wearing like a flammable, protective suit or anything. He's just wearing typical deck crew. He had a very dangerous job. It's actually the most dangerous job in the world by the numbers, working on a Navy deck crew. It's still incredibly dangerous. I want to turn to talk about submarines as we're getting ready to start closing out some. World War II, another submarine war. The major submarine war that most people know about is the Battle of the Atlantic. The Battle of the Atlantic is the longest running naval battle in history. The Battle of the Atlantic goes from September 1st, 1939 until April of 1945. It is the entire Second World War, a war at sea in the Atlantic. Germany's U-boats trying to prevent the United States from sending war materiel and support across the Atlantic to our allies in Britain and sending war material to our allies in the Soviet Union. There's a race. Germany's trying to stop that buildup. We're trying to carry it out. Germany's U-boats. Now, the German U-boats of the Second World War are a bit different from the first. The main German type of U-boat used in World War II is called the Type 7. There's some weird things about it. I'll just mention a few briefly. It still uses those diesel engines on the surface, still uses the electric batteries when submerged. The Germans had played with the technology enough to where this thing, if it was running submerged at a very slow speed, it could stay down for a little bit over 24 hours. They've played with the technology enough that they've gotten some extra mileage out of it. Some weird things about the design though. On the prow of this submarine, you see this kind of weird shark tooth, saw-looking thing. A lot of people say, what is that for? I mean, it looks kind of cool. The Germans like cool-looking weapons, but why is that there? The Germans had this belief that the British were going to string harbor nets across the entrances to their harbor. And the German submarines didn't want to get tangled up in those nets underwater. And so they said, well, if we just develop this thing, we hit those nets, maybe we can sort of saw our way through. It didn't really work, but it was an attempt to get around an existing problem. So these German Type 7 U-boats are basically like World War I German U-boats, but improved and on steroids. They're technologically very similar in some ways to the U-boats of the First World War. There's very few of these left. One of them is in Chicago. If you ever get a chance to go to Chicago as a tourist and you have a few hours to kill, you go to the Museum of it's National History. You go to in Chicago, this museum, they've got this U-boat on display, U-505. You can walk through it. Really interesting, last time I was there, there's almost always, by the way, you go to a military museum or something, there's almost always some old guy standing there. Always take a chance to talk to the old guys because they have many times actual experience with this stuff. And the last time I was there in Chicago, I was visiting my brother, who's a professor at Champaign-Urbana, University of Illinois. I met this old guy here, and I just started talking to him. This was years ago now. And as we were talking, it became apparent very quickly, he's not American, he's actually German. And so I was talking to him. He actually was a U-boat crewman, not on 505, but he had been a U-boat crewman during the war. And so a lot of what I know about German U-boats and what it was like on them in the war, I mean, I've read a lot, obviously, but you can't beat talking to people who are actually there. So if you get into U-505, come down this ladder from the conning tower, which is up there. This is the high-tech control room of the 1940s. There's no computers. It's all hand-cranked knobs and dials. You've got your elevation control and your helm right here. It's where they steer the ship from and they can go up or down.
What country was the U-5 made?
Made in Germany. It's a German U-boat. Over here is where your captain would stand. He's got his plotting table so he can look at the map, figure out where he wants to try to position his submarine. These right here are the periscopes. That's his attack periscope. You raise, you lower it. Really only two ways in and out here, aside from up or down. That's back, towards the back end of the ship. There's a hatch just like it at the front. This is the most technological room on a German Type 7 U-boat. This is the height of technology in the 1940s. What you've got is a radio. You've got a sonar set for listening to ship engines at distance. That's it. This thing is basically the size of a broom closet. And so the way this would have worked is they would have just had a little curtain separating it, and the most high-tech room on the German U-boat is right there. Forward torpedo room. You have 4 torpedo tubes. There actually is a dud torpedo they've kept for display purposes. One of the things that this old guy told me as we were walking through here, he said, this is nothing like experiencing a German U-boat for real. I was like, that's interesting, why not? He said, see how clean this is? It's pristine. I mean, they polished it. He said, if you get into one of these boats for real in the 40s and you were in the Battle of the Atlantic, there would be food, canned food, all sorts of things suspended in nets from the ceiling because they have limits and things on submarines. And he said there were about 20 to 30 men who this was not only a torpedo room, but it's their berthing area. So people are sleeping on little mats on top of torpedoes and things. He said it was just chaos in there. Nothing at all like this museum. This is the engine room of 505. You can see the diesel engines right here. The batteries for the electric engines are on the outboard sides. The guy I talked to was actually an engineer on the U-boat he'd been in. And he said that after about 10 minutes being in this, if you were running on the surface, you'd be absolutely deafened just because of the reverberating noise inside the steel hull from those engines. I thought this was an amusing story, so I will share this rather gross story with you. The one room that everybody on the submarine, captain to the lowest guy, everybody would have used is the head, right? It's the latrine, the facilities, however you'd say that politely. This is it for about 60 to 80 guys that got one toilet. And as I was talking to this older gentleman, he told me, he said in the German Navy and the Kriegsmarine, he said we had a rule. It's called the 25-meter rule, and nobody from the captain to the lowest man would ever violate this rule. And the 25-meter rule said this: if you're in a submarine, a German U-boat, and you were submerged and you were more than 25 meters deep, nobody was allowed to touch that and flush the toilet. The reason being that the water pressure from the outside of the submarine was greater than the flush pressure, and if you flush that, the water from the outside would flood into the submarine, and this would just erupt inside the submarine. It's really nasty. So nobody would flush the toilet. And I said, well, what was that like? He said, well, the longest that we were ever down on the submarine I was in, he said, we were off the western approaches, which is near Ireland. He said, we'd been down for almost 27 hours. And it finally reached a point where the captain said, all right, nobody else is even to go into that room. because we don't want it to, the toilet to overflow. We'll just have to wait until this convoy moves on. So, I mean, this is kind of, it's history, though. You'll never read about it in a history book. I've never read about the 25-meter rule in any of the history books, but wow, what a piece of history, right? So, further technology in the Battle of the Atlantic. The Germans got really, really good at this. The Germans got super good at this, so good at it that by 1942, when the Americans came into the war, the Germans had U-boats that were prowling just off the coasts of the United States. I was talking to several people in here. There's one of them that sunk about 12 miles from Cape Hatteras in North Carolina with a lighthouse. There's a sunken German U-boat in World War II about 12 miles from that spot. German U-boats right off the coast of America, sinking all sorts of shipping as America entered the war. So the Americans and British got busy trying to protect their merchantmen from these German torpedoes. And they tried a lot of interesting stuff. And this is one of the examples of what they tried. You have a merchantman sailing along. They're afraid of getting hit with a torpedo. And so you take these chains and you attach them to shrimp boat arms. You've seen the shrimping fleet at Charleston. Same thing here. You have the shrimping boat arms. You run these chains in the water parallel to the ship. And the idea is, well, if a torpedo's coming in, it's going to strike the chain and knock the ship. That's a good idea, right? Anybody who's ever been on a ship, last year I taught this, I had 2 ex-Navy guys who saw this and were like, that would never work. Yeah, it actually turns out not to work. It's a good idea. The reason it doesn't work is that these chains, fishtailing through the water as the ship moves, tend to drift inboard, and they can get fouled and caught in those propellers. Brings the ship to a halt. So it's a good idea that doesn't work. So what they have to rely on instead are technologies which allow them to target and sink the U-boat. You've got these new technologies. Sonar, radar is going to come out in World War II as well. Sonar is the ability to detect an underwater object through sound. There's 2 types of sonar. There's active sonar and there's passive sonar. Active sonar means that you have an ability to project sound waves into the water, sort of a very loud noise. Bing! And as you make that noise, as the sound waves go through the water, if they strike a submerged object, a hard thing like a submarine, those sound waves reverberate. They bounce back off of it. You get a return sound, and it lets you know that there's something sitting submerged in the water there. That's active sonar. Passive sonar is what these guys are doing. The U.S. Navy destroyer in the Atlantic in World War II, they're listening. They're listening for the sounds of an engine, a German electrical motor running below the surface of the water. Pretty good giveaway, that's a submarine. They're listening for sounds like a hull popping and creaking as the submarine changes depth in the water, and the water pressure either increases or decreases on the hull. They're listening for these things actively. And so we're sort of simplifying this here. There's 2 main types of sonar. But what we can say about this is that this is extremely difficult and technical, right? I'm not going to get too technical here with you. But one problem that you always face with sonar, whether it's active or passive, has to do with something called the thermocline layer. It's a temperature gradient that exists in the water. Shallower water is warmer, deeper water is colder. Right there at the thermocline layer, there is this transition or shift in the water's characteristics in terms of the way that sound passes through it. And so if you're a submarine captain and you're below that thermocline layer, it makes the sound of your engines and things distorted as it passes through that temperature change. It's the details like this that you have to understand and you go to school for years for if you're going to become proficient with the technology. World War II radar. Radar becomes a big thing in World War II. Radar has the ability to detect a submarine on the surface. Why would that be important? Well, as I told you, these submarines cannot stay down indefinitely. They have to resurface to recharge their batteries. And so early in the Battle of the Atlantic, German submarine crews would surface at night. They stay down during the day when they could be seen with the naked eye if they're on the surface. And at night, they come back up and they start their diesels and recharge their batteries. Well, by the time you get to 1943 or thereabouts, middle of the war, most US and British ships have radar, which means that you can see on your radar screen if suddenly there's a blip, if suddenly there is something on the surface of the water which was not there the last radar sweep through. It's a German submarine who's just surfaced. He might be 50 miles away from you over the horizon and blacked out at night. You're not going to see him with binoculars. But you can pick him up with this. Suddenly he can't hide anymore. The other technology, MAD, it stands for Magnetic Anomaly Detection. They figure out in World War II that submarines, because they are chunks of metal, they give off a magnetic spike. If you have the ability to detect that magnetic presence in the water. And so this is an example of a British Royal Air Force aircraft. It's got this hula hoop looking thing around it. That's a magnetic anomaly detector. And if you fly very low over the surface of the water, you're getting no reading, no reading, no reading, and suddenly, boom, there's some magnetic anomaly below the surface of the water. It makes your compasses go all funny for a minute. It's such a magnetic presence. It's a submarine, it's running submerged. And so all these technologies, sonar, radar, MAD, they take away what had been the submarine's greatest asset, which is invisibility. And the Battle of the Atlantic shifts, because suddenly German submarine captains cannot just surface their submarine at night and be like, well, we're untouchable. Suddenly you've got this situation where they're able to be attacked day or night. The hunted become, well, the hunter becomes the hunted, right? German U-boat captains have lost the initiative. So late in the war, right, there's always this pushback. Technologies like this, military or otherwise, you've got the Allies developing new technologies to marginalize the submarine. That starts to work. So the Germans, by 1944, late in the war, start saying, how do we get the initiative back? How do we make it so that we have the advantage? They come up with this. Again, if you don't read German, that word just means snorkel. You have a metal tube that a German submarine can run when he's submerged, and he can run his diesel engine below the surface of the water. It's basically just an exhaust pipe. Allows a German submarine captain more flexibility. He can now run the diesel engine while his boat is submerged slightly. New torpedoes that the Germans come up with, the LUT and the T4. The LUT is sort of a development of an existing idea. The idea with the LUT, if you're a German submarine captain, is you surface and you see a convoy. Convoys steaming this way with those arrows, all these merchant ships. It's really tough for you to get a shot off because maybe there's destroyers or airplanes nearby. So if you're a submarine captain, you pop up to the surface, just below the surface, and you fire a LUT torpedo. And it runs this preset pattern back and forth through the convoy. And the idea is that hopefully you're going to get a hit on somebody. You're not really aiming at a specific ship, it's an area target, basically. And you're just firing this LUT torpedo in the hopes of doing this. It's an advantage to the German submarine captain because when he fires it, all he has to do is get back down really fast. And hopefully he gets his hit. The other one, the T4, very, very few of these are built in World War II. And it's a good thing too, because the T4 was revolutionary technology, in my opinion. The T4 was the first torpedo which we can call an acoustic homing torpedo. The Germans put a mini sonar suite into the T4, allowing it to home in on the engine noises of certain vessels. And so a German submarine captain didn't even need to use a periscope anymore. If you heard an American destroyer overhead, you just fire a T4 into the water in the general direction, and if it's in its cone of availability, it picks up on the engine noises of that American destroyer and it's capable of sinking it. Also late war, the Type 21. This thing was a huge leap in technological capability, the Type 21. This is modern in every sense of the word. The electrical engines of this thing had the ability to propel it at high speed while submerged and to stay down for days on end. This thing can stay deep indefinitely, very difficult to detect using sonar. You combine something like a Type 21 U-boat with a T4 torpedo, the Battle of the Atlantic swings back the other way. Almost done with World War II submarines. Project Ursul, late 1944. The German Kriegsmarine, like the rest of the German military, realized that they were losing the war. They start developing all these new technologies, the Type 21, the T-4 torpedo, and Project Ursul. Project Ursul was an attempt to take existing rockets, like the V1, like the V2, take existing long-range rockets and be able to fire them from submarines. Why is that useful? Because the thought process was, if we can take a German U-boat and park it off the coast of Virginia some late night, you orient this thing properly, we can hit Washington, D.C. We can actually strike the American homeland from far across the Atlantic. We can maneuver close with a submarine and deploy this type of firepower on target. The Germans experiment really heavily with this, 1944 and 45. Now, fortunately for the world, the Nazis had already lost the war. They just didn't realize it yet. They lost the war for a variety of reasons, but these war-changing technologies were just too little too late. If you look at 1945, just before the surrender of Nazi Germany, Germany is winning the Battle of the Atlantic again. Those T-4 torpedoes especially were beginning to make an impact. That's an American Fletcher-class destroyer. It's been broken in half by a T-4 torpedo. Fortunately for us, the Germans just didn't have enough of them to win the war. And so the Germans lost the Battle of the Atlantic. So after World War II, submarines remained critically important because of the Cold War that followed. As 1945 came about and World War II ended, both the United States and the Soviet Union were looking at Nazi Germany with that kind of technology and saying, we want that. We have to have that. And so there was an operation, an American operation called Operation Paperclip. The Russians had their own version of it, in which they had teams of scientists and people like that going through Nazi Germany and trying to grab all the records they could of top secret programs like Project Ursul. I showed you a picture of Project Ursul a minute ago. 1948, USS Kursk, a result of Operation Paperclip. What are you seeing here? 3 years after the end of World War II, an American submarine, which is about to do trials launching a long-range cruise missile. And those of you who know weapons and stuff, if you look at that, you know what it is. Some of you may not. That's a German V1 flying bomb. It's been captured by the Americans. We've repainted it. We've put our little symbol on it. But it's a testing platform. We get that Project Ursul data, and we're like, yep, we're going to run with that. That looks like something that's potentially useful. Now, it didn't always work really well. USS Kursk launched this thing, and it then, because it was an old German V1, it spun out of control and exploded. But within a few years, we were able to get this down. We succeeded. We were able to actually figure out how you launch ballistic weapons from a submarine. And so you enter into this era of world history in which you have the emergence of multiple new technologies that change everything. An American submarine, USS Nautilus in 1954, is the first nuclear-powered submarine in the world. They use a nuclear reactor on board this thing in 1954. And the reason that this is significant is that no longer does this type of submarine have to surface. It can run subsurface indefinitely. It can cruise around the world multiple times and never have to come to the surface. And people say, well, what about the breathable oxygen? Well, tied in with the development of nuclear reactors and submarines, they came up with technology that allowed them to pull oxygen out of the seawater around the submarine and turn it into breathable air. So today, when you have a U.S. Navy submarine that sails out of port, a place like Kings Bay, Georgia, where a lot of our SSBN fleet is based on the East Coast, those boomer captains, when they clear the harbor, they go down, and that submarine's not going to come back up for 6 months. They're going to stay submerged for 6 months. They're cruising somewhere in the world. Even the President of the United States doesn't know. That captain goes where he wants, and he has access to this type of technology, the ICBM, or Intercontinental Ballistic Missile. This is an Ohio-class SSBN. SSBN stands for Submarine Ballistic Launch Nuclear. It's nuclear-powered ballistic missile launching submarine, Ohio-class. Each of these tubes contains an ICBM. This is the culmination of that whole Project Ursel thing that we took from the Germans. You launch something like this from a submarine, it goes up into outer space. It's a Trident ICBM, if you care about the name. Yeah.
What does ICBM stand for?
Intercontinental Ballistic Missile. You shoot this thing up, you can target anywhere in the planet with it. This thing goes into outer space, the nose cone comes off,